Okay, now see, today it is AC circuit which is having only capacitor. Okay, so you will have an AC circuit, okay, which is only having capacitor in the circuit this way. Okay, so now this will periodically become positive, negative. Once it is positive, then this is negative, and this becomes positive plate, then the other becomes negative after a certain interval of time. Here the voltage, try to understand, applied is V is equal to, always we have Vm sine omega t. So voltage source is always same, Vm sine omega t. Okay, so this is the circuit which is having only capacitor in it. Okay, and as you know, this becomes positive, negative, periodically the capacitor will become. Okay, and the voltage source is Vm sine omega t. Now see, when a capacitor is connected to a voltage source in a DC circuit, current will flow for the short time required to charge the capacitor. Okay, that is the main difference. As charge accumulates on the capacitor plate, the voltage across them increases, opposing the current. Okay, when the capacitor is fully charged, the current in the circuit falls to zero. This becomes in the DC circuit. In AC circuit, the plates are periodically getting plus and minus charge. Okay, so it is joined with the AC. It limits to regulates the current but does not completely prevent the flow of charge. Completely doesn't become zero. The capacitor is alternately charged and discharged as the current reverses after each half cycles. Okay, so for one half cycle, this plate becomes positive, this becomes negative. After that half cycle, this becomes negative, this becomes positive. So this periodically charging and discharging the capacitor takes place. Now try to understand, very easy again. We have to apply the Kirchhoff second rule. Here the voltage source is how much? Vm sine omega t. So if this is minus and this is plus, at an instant when you are applying the Kirchhoff rule, then this becomes positive, this becomes negative, and as you know that voltage across capacitor, as you know, V is equal to Q upon C. Okay, and you are going from positive to negative, so it becomes minus Q upon C. Here small q is taken, and that is equal to 0 if you apply the Kirchhoff rule. So it is written like this. Okay, it is given here Vm sin omega t minus Q upon C is equal to 0. So Vm sin omega t is made subject of formula. Okay, and C is then multiplied to the left hand side. So C into Vm sin omega t is equal to Q. Now as you know that I is equal to dq upon dt. Okay, so we are taking the differentiation of this particular equation to find the current. So dq by dt is equal to C and Vm are constant. Okay, then we have to take the differentiation of sine omega t. Okay, and as differentiation of this sine omega t is nothing but cos omega t, and omega is to be multiplied, so this becomes C Vm omega cos omega t. So this you are getting, okay, Vm C omega into cos omega t. So I is written in a different way. This is say I. Now if you write it in a different way, okay, then this C and omega which are there in multiple, they are taken in the denominator's denominator. So it has been written in this way: Vm cos omega t upon 1 upon omega c. Okay, so it is written in a different way only, and instead of this cos omega t, it is written as Vm sin pi by 2 plus theta. Sin pi by 2 plus theta is cos theta, so it is written in a sine function pi by 2 plus theta. Theta means omega t upon 1 upon omega c is then taken as xc, which is known as reactance. Okay, so the value of the current will be this Vm sin omega t plus pi by 2 upon xc. Okay, so it is just written below. Okay, and Vm upon 1 upon omega c is taken to be Im. So what is the difference now? See, Vm upon 1 upon omega c, or we can say Vm upon xc. Vm upon xc is taken as Im. So we can write this equation. As I is equal to Im sin omega t plus pi by 2. This way it can be written, where Im is nothing but Vm upon xc, and xc, as you know, it is 1 upon omega c, which is called capacitive reactance. Okay, which is called the capacitive reactance. Okay, so it can be easily understood. Xc is 1 upon omega c, it is written here, which is known as capacitive reactance, and Im is Vm upon xc. Okay, SI unit of this xc will be ohm. Okay, the capacitive reactance limits the amplitude of current in purely capacitive circuit, or it does not allow the increase in the current in the circuit. Okay, so it behaves as a kind of resistance, as it resistance opposes the current. Now if you draw the phasor diagram of this, okay, so phasor diagram can be drawn easily. Okay, see, first of all we draw this vertical and horizontal axis. Okay, now voltage is given by any time Vm sin omega t. So this is the phasor of voltage whose magnitude or length is taken to be Vm, and at any time, say it is at any time omega t1. Okay, the angle whatever it makes. Okay, now see, the current is leading here. Try to understand. The equation of current is nothing but I is equal to Im sin omega t plus pi by 2. So it is the angle omega t plus pi by 2. So the angle has to be more by 90 degree than pi by 2. So this will be the phasor of electric current. Okay, so this is the phasor of electric current, and we can say there is an angle of pi by 2 between voltage and electric current. Okay, now both the functions are sine function. Try to understand, for current also and for the current also and voltage also. Now see, for voltage we can easily draw the sine function. It is Vm sin omega t, so sine curve we have to draw. So this is the graph for voltage. Okay, now see, this is sine omega t plus pi by 2, means it is a curve, or rather we can say it is Im cos omega t. Try to understand, pi by 2 plus theta is cos theta, so the graph will be of cosine curve, and pi by 2 is the phase difference, so we can draw like this. Okay, there is a phase difference of pi by 2. Okay, so here this shows the phase difference of pi by 2. Okay, so this is the graph of voltage and this is the graph of electric current. Okay, where you can see the phase difference between voltage and current to be pi by 2. Okay, and voltage at any time, that also can be given. Here voltage is, say, at any time omega t1, that is instantaneous voltage, and the value of instantaneous current at any time is also obtained from this graph. This way you can show. Okay, so this way, first of all you have to draw the phasor of voltage, then at 90 degree the phasor of current. So these two phasors are obtained. Now for voltage it is sine curve only, so we have to always draw the sine curve for voltage. Now here for current it is sine omega t plus pi by 2, plus pi by 2. So it is a cos curve. So cosine curve begins from maximum and it becomes 0 and then it goes in the other direction. So this way we have to draw the cosine curve. Okay. So this is very easy to draw once you practice it 2-3 times. Okay. So this can be shown in this particular figure. Okay, which is given in the textbook also properly. Just we have to practice 2-3 times. Okay. Now we can say that here current phasor is pi by 2 ahead of the voltage phasor. So there is a phase difference of pi by 2, or we can say there is a phase difference of 1/4 of periodic time. 1/4 of periodic time. This can be understood easily. It is t by 4. Okay, so we can easily calculate this value of t by 4. What is that? Pi by 2 omega. Okay. Now we talk about the power in this circuit. Okay, power, instantaneous power is nothing but current into voltage. Okay, current we have just now found, it is Im cos omega t and the voltage is Vm sin omega t. Okay, this is very easy to understand. Just we have to multiply both. So Im Vm cos omega t sin omega t, it is similar to that of inductor. Just we have to multiply by 2 and divide by 2. So 2 cos omega t sin omega t and it is divided by 2. So this becomes sin 2 omega t, as 2 cos omega t sin omega t is sin 2 omega t. Now if you find the average, then average power is nothing but Vm Im, they are constant, divide by 2, all these are constant quantity. Average of sin 2 omega t over entire period will be equal to 0. So the power, average power on the entire period or entire cycle will be equal to 0. Okay, so the average power in this circuit will be equal to 0, as we have discussed in the inductor. Okay, now we shall have the LCR circuit, very important topic of this particular chapter. Okay, we will have LCR circuit, means 3 components: L, that is inductor, capacitor, C, and resistor, they are joined in series. Now see, total voltage here which is applied, that is AC voltage, which is divided into 3 segments, because in series the voltage is divided. So VL, VR and VC are the 3 voltages across inductor, resistor and capacitor. Now as you know that voltage across inductor is L di by dt, voltage across resistor is I into R, and voltage across capacitor is Q by C. So it is applied, just a Kirchhoff rule is applied. Okay, and we can write the total voltage V is equal to L di by dt plus IR plus Q upon C. This is very easy to understand. Now these are the different potential difference which are shown. Potential difference across inductor is L di by dt, potential difference across capacitor is Q by C, and potential difference across resistor is I into R. So this is a general equation of total voltage which is applied in the LCR circuit. Now we are having the phasor diagram solution of this LCR circuit. Now try to understand here, the current which is passing through this circuit is generalized. It is taken as I is equal to Im sin omega t plus phi. Okay, because in inductor the current was lagging behind, it was minus pi by 2. Okay, in that capacitor it was omega t plus pi by 2, and in only resistive circuit the current and voltage were in phase, there was no phase difference. So here the current which is passing through the circuit is taken to be I is equal to Im sin omega t. So current in each element of this resistor, capacitor and inductor will be same. Why? Because they are in series. Okay, here phi is the phase difference between voltage and current. What is phi? Phi is the phase difference between voltage and current. Okay. Now see, the voltages across this inductor, capacitor and resistor are VL, VC and VR. Right now it has been shown by a vector. They are not the vector quantities, but to show them as a phasor, okay, because we want to show them as rotating vector, that is why it is shown in a this phasor way, or rather vector sign is made. Okay. Now see, VR, try to understand, voltage across inductor, capacitor and resistor are this. Now voltage across resistor is parallel to I because there is no phase difference. Then voltage across capacitor is pi by 2 behind that of I, and VL is pi by 2 ahead of I. So if a phasor of current is drawn, then say this is the phasor of current which is making an angle of say omega t1 with the horizontal axis. Okay, this is the phasor of electric current. Then voltage of resistor is having no angle between I, means there is zero angle or they coincide. VR is in this direction, but as VL is ahead of this and VC is behind, therefore VC will have 90 degree behind and VL will be 90 degree ahead. So this will be the phasor of voltage across inductor, and this will be the voltage across the VC is pi by 2 behind. Okay, so this will be the voltage across capacitor. Okay, so just see it here. It has been explained very nicely. Just you have to understand the drawing only. See, this is the phasor of electric current. Phasor of voltage across resistor is in the same direction of electric current. Now voltage across capacitor is behind the current I. Okay, so voltage across capacitor is drawn in this way, and voltage of inductor is drawn in this way, that is ahead of current I. So this is voltage of inductor. So all the phasors are shown. This angle is say omega t plus phi at any time. Okay. So this is very easy to draw once you draw it properly. The amplitude of phasor, they can be voltage across resistor is nothing but current into resistor. So voltage across resistor will have IMR, then voltage across capacitor will be Im into XC. This is just a Ohm's law. Voltage across capacitor, voltage is current multiplied by resistance. So this is current multiplied by resistance. This is also current multiplied by reactance. Reactance behaves as a resistance. And voltage across inductor is Im into XL. Now this is the equation which we had. Okay. So total voltage is VL plus VR plus VC is equal to V. Okay. Here VL is L di by dt. VR is IR. VC is Q by C. So if you want to show only try to understand only the representation of voltage, okay, then representation of voltage can be easily done. See, this is your horizontal line. Voltage across resistor is VR. This is voltage across resistor VR. What is the angle of this voltage across resistor at any time? It is omega t plus phi. Try to understand. This angle is omega t. Yes, it is voltage across resistor. Okay, that is omega t plus phi. Okay. Now see, the voltage across here, this voltage was across VC, that is voltage across capacitor. This voltage is across inductor, voltage across inductor. Now try to understand. The resultant of VC and VL, one vector is in this direction, the other vector is in this direction, then the resultant will be, say this is 10, this is 3, then resultant will be 7 in this particular direction. So resultant is drawn in this way. See, Again I am drawing it for you. Say for example, this is your horizontal line. Okay, this is the phasor of voltage across resistor. Now the resultant of this VC and VL, that will be VC, just vector sum VC plus VL, as such this is a vector sum. Okay, resultant of this. Okay, otherwise the magnitude will be VC minus VL, that will come in a later case. Okay, so these are the two. Say for example, these are vectors only, just you take them as a vector. So now if you want to find the resultant vector of this, then what will you do? Then just we have to complete the parallelogram. Okay, so this will be the resultant vector, or just we use the Pythagoras theorem, then this will be the value of resultant vector V. Okay, so this is VR, this is resultant of VC and VL. Okay, that is as such VC minus VL, say this side it is 10, this side it was 3, so it is resultant 7. Then you complete the parallelogram, or you just use the what you call it, Pythagoras theorem. These are at 90 degree to each other. Okay, then this value of voltage, resultant voltage V, you will get. Okay, and that is explained here. Okay, VC minus VL, see it is written here. See, it is taken as VC minus VL, or VCM minus VL, or it is taken as resultant, because VC is more than VL. This side the length is smaller, this side the length is bigger, this side. Okay, so VC minus VL it is taken, or VCM minus VLM it is taken. So resultant will be VR square plus VCM minus VLM the whole square. This is its magnitude. What is the length of this? The length of this particular segment is nothing but VCM minus VLM, that is the length, or rather its magnitude. Okay, so now if you want to find the resultant value, then square of this plus square of this, and then square root you take. Pythagoras theorem just we have to apply. Okay, so it is considered, or it is taken this way. Okay, so it is Vm square, that is resultant value Vm square is equal to Vrm square plus Vcm minus VLM the whole square. Now Vrm is nothing but Im into R, Vcm is Im into Xc, then VLM is Im into XL. Okay, the whole square it becomes. Then Im is taken as common. Okay, Im is everywhere, you can see. So Im is taken common. Okay, just you can see it properly. Okay, Im is taken common, so it becomes R square plus Xc minus XL the whole square. So we can make Im square as a subject of formula Vm square upon R square plus Xc minus XL the whole square. And if you take the square root, then you will get Im is equal to Vm upon under root of, this can be written as under root also, or you write raised to 1 by 2. Okay, it can be written as R square plus Xc minus XL the whole square raised to 1 by 2. Okay, here this value which we got, see this is again an Ohm's law, try to understand. This is voltage upon resistance, and this value here is known as impedance of the circuit. Resistance નું નામ પડ્યું છે, it is taken as Z. Okay, which is taken as the impedance of the circuit. It is nothing but a kind of resistance. So Im which we got here, Im is equal to Vm upon Z. Vm upon Z we can write, is again Ohm's law for the series LCR circuit, and it is taken in this way. It is again shown in the Pythagoras theorem way. Okay, say this is your resistance R, this is Xc minus XL. Okay, then this will give you the resultant value Z. So we can write R square plus Xc minus XL the whole square and square root of it, that will give you the value of z, which can be shown. And the angle here is phi, that is the angle which is made by the resultant value z with the resistance. Okay, so now if you want to find tan phi, then easily it can be found. Tan phi is opposite upon adjacent xc minus xl upon r. Okay, so tan phi can also be found. Okay, or VCM minus VLM upon VRM, whichever way you want to find, you can find. Okay, here you can see, if you want to find the value of tan phi, then tan phi is nothing but VCM minus VLM. See, here you can see in this figure, this is the angle phi. So opposite, it is VCM minus VLM upon adjacent. Okay, so it can be easily found VCM minus VLM upon R. Okay, so you can find the value of tan phi. Okay, so tan phi is VCM minus VLM upon VRM, so it is XC minus XL upon R. Or we can just find the angle with the help of this equation. Phi is equal to tan inverse XC minus XL upon R, and this value is known as impedance of the series LCR circuit. Okay, try to understand 2-3 times and draw them 2-3 times, then and then you will be able to understand. Okay, thank you very much.